So we have finished our first unit, and you guys have taken your first exam, and we're still waiting to find out how that went. As soon as I finish this video, I'm going to go back and finish grading those. Hopefully I'll have those in before the end of the evening, by Tuesday afternoon at the latest. So this next unit, we are talking about random variables and sampling. So we've looked at the general basics of statistics, and now we're going to start trying to get into more of the applied statistics. You've seen plenty of applied examples based off some of the basic things that we've already looked at, such as standard deviation, some basic probabilities. We're going to lead up through this section or this unit, and then we're going to start looking at what's called bivariate data, where you have multiple variables, as opposed to where we're used to univariate data, where we just have one variable. The other thing too, before I go on and jump into these notes, please remember to be thinking about your project. The project that you guys started a couple weeks ago, you presented me with your proposals for your statistical study. And I know some of you have probably kind of put that off to the side. I know life, you get a little bit busy, but remember that will take place of either your second or third exam. I have not decided yet, but most likely it will be your third exam, and then you'll have your final exam, and then this class is over. So talk with your groups, talk with your partners, get this project moving. You need to start collecting that data. Because what we're going to start looking at now, you may need to apply some of the things we look at over the course of this next unit to your statistical study. Sorry about that. So you can see from the heading here, we're talking about discrete random variables and probability distributions. Discrete random variables, it sounds like a daunting and intimidating term. A lot of things in statistics sound that way, but this is not necessarily the case. A discrete random variable is going to be something that you can quantify. It is representative of a population, and we're going to first introduce it here through example, and then we'll discuss it in a little bit more detail. So we've looked at an example like this before. In a previous section of notes from the first unit, where we have the number of siblings and the frequency in some given class, and then we also have the relative frequency there listed in the right hand column, and it says discuss the number of siblings in the context of randomness. Well, the number of siblings will vary from student to student. So if we were to select a student from random from this particular class, there's a chance that that student could have either no siblings, one sibling, 2, 3, or 4 siblings. And that is kind of the heart of a discrete random variable. It is strictly decided by chance. So this variable, in this case, we're going to say it's X. If I pick one student out of that class, the number of siblings they have is left to chance, because they could have anywhere from 0 to 4 siblings. And that's kind of the core concept of a discrete random variable. It can change depending upon the sampling that you do. So first of all, a random variable is a quantitative, so remember that has a number attached to it. It's a quantitative variable whose value depends on chance. So that just depends upon the sampling method, how the group is sampled. So going back to the siblings there, if I pull one person out of that class, again, they could have any number of siblings from 0 to 4 based off the information obtained from that class. We're going to skip through this, just kind of defines a couple more examples of discrete random variables. Here we have a more precise definition. A discrete random variable is a random variable whose possible values can be listed, so it is finite. If we can list all the possible values, it's finite, and then that means we can have a discrete random variable associated with that particular population. If it's an infinite set, then we don't have that possibility of having a discrete random variable, because we don't know all the potential values that could exist. When we talk about random variable notation, we still use the lowercase letters to represent a typical variable. When we use a uppercase letter, that's our discrete random variable. So the number of siblings, in this case, from the previous example, we would use the big X. The little x would be the actual number of siblings that a given student has. So the notation you can see right here, if we want to look at the probability that a randomly selected student has 2 siblings, we can represent that with big X equals 2. So our little x is 2. Our discrete random variable is the uppercase X. And then we wanted to look at the probability of that event. It's going to be P of X equals 2. And we're going to look at how to calculate these here in this next example. We're going to go back and look at distributions and histograms again. We looked at that at the very beginning of Unit 1, so we're going to be using Google Sheets again to compute some things. I'm going to use it here in a couple of our examples through this first set of notes. Probability distribution. It actually is going to correspond to a frequency distribution. The values are going to be identical. We're giving it this new term, or this new name, probability distribution, because we are referring to the probabilities of these events happening. And then the probability histogram is going to be the same thing that we looked at previously when we looked at the frequency histogram, but now we're looking at the individual probabilities of each event. And that's going to bring us into example 2. Now, example 2 does refer back to the first example at the beginning of the notes with the number of siblings that a particular student may have. So for part A, it says determine the probability distribution of the random variable X. And that is going to be a case where, let me pull up Google Sheets. So here is our table. I've just typed it into Google Sheets. I have the column for siblings. I have the column for frequency. And I just want to figure out what are the distributions for this particular set of values. So I'm going to go back to our notes first and just do a quick example of how this is calculated. So we're looking at part A, and it says determine the probability distribution of the random variable X. Well, earlier, prior to getting to this example, we talked about when the probability of X equals 2. So in this case, we're looking at what is the probability of a randomly selected student from that given class has 2 siblings. And the way we calculate that is it's the frequency over the population. Remember, big N represents the population, and then that little f is our frequency. So when we figure that out, the frequency for the number of students in that particular class that have 2 siblings is 11, and the population is a size of 40. So when we simplify this into a decimal to get our probability, 11 over 40 will reduce to 0.275. So the probability for a random student having 2 siblings is 0.275. That's just for one value. We want to find, for the probability distribution, we want to find all the values, and that's where Google Sheets will come in and make things kind of handy when we're looking at this. So you can see on the screen here I have the number of siblings in the first column, the frequency in the second column, and I want to find the probability distribution. So I neglected to indicate this column, so I'm going to put P of X equals X. That's going to be my probability distribution column, and it's just going to be a simple equation. It's going to be the frequency divided by the population. In this case, we know the population is 40, and I'm going to just drag that across all the values, and we get these values right here for the probability distribution of the number of siblings that any random student may have. And we looked at 2 on the example, and you can see right here that 2 does in fact equal 0.275. So that worked out really well for us. The next thing we want to look at is part B, where it says construct a probability histogram for the random variable X. So remember, when we did probability or frequency histograms, we looked at relative frequency and we looked at frequency. Relative frequency was always going to be a decimal value. Frequency was a count. Google Sheets struggles with doing an accurate relative frequency histogram, so When we're doing the probability histograms, we're going to do the same thing we did in the previous unit. We're going to use the siblings and we're going to use the frequency to come up with our histogram, because the shapes are going to be the same regardless of whether we use relative frequency or, in this case, probability distribution and frequency. The two graphs are going to be similar. The only difference is the y-axis will have different values along its length. So we highlight siblings, we highlight frequency and their associated values. We're going to go to Insert Chart. It's going to happen. There it is. And remember, we want to change this to a column chart. And there is our histogram for frequency and siblings. And you can see, if we kind of try to visualize this curve right here, this does appear to be a right skewed set of data. We would expect that to be true. Fewer people are going to have a larger number of siblings. You're going to have more people with 0 to, well, in this case, it looks like 1. It's unimodal, so we have that one peak in the graph. And it is right skewed. So there's our histogram for example 2. When we go to discuss this a little bit further, the discrete random variable x, that's big X, is going to be the sum of all the probabilities. And that should always be equal to 1. If the sum of all your probabilities does not equal 1 for any variable, then there's a miscalculation somewhere. It could be you miscalculated the population size, or there could be an error with calculating the probability distribution. So anytime you do this, you can always add up, and I'll show you here on example 2 real quick. Let's go back to it. I have this column, this probability column. If I take that and I sum this column of values, you can see that it does add up to 1. So the probabilities on this one are accurate, and because the whole thing does add up to 1. If it adds up to anything other than 1, there's a calculation error somewhere that needs to be corrected. Can it be slightly above 1, slightly less than 1? Yes, but it's going to have to be very minuscule, because it could be due to a rounding error based on the computational techniques used by Google Sheets in this case. It could be 1.01, and that's going to be fine. It just means there's a rounding error somewhere. You don't want to see something that says 1.3, 1.4, or 0.75. Those would be inaccurate, but relatively close to 1 is going to be acceptable. For example 3, we are given this information from the National Center for Education Statistics. It shows a frequency distribution for the enrollment by grade level in public elementary schools. Kindergarten is equal to value 0. Then we have 1 is first grade, and so on. Frequencies are represented in thousands of students. So we want to take this. So if you can look at kindergarten there, it says 4,819. Which means there's 4,819,000 students that are in kindergarten at the time of this data being collected. And here on the right, we have let capital Y denote the grade level of a randomly selected elementary school student. So then Y becomes a discrete random variable, and the possible values are all the little y's, which are 0 through 8. Part A, use random variable notation to represent the event that a selected student is in the 5th grade. So there's nothing fancy to this. It's just simply a notational question. For part A, we want to use random variable notation to represent the event that a student is in the 5th grade. So capital Y is our discrete random variable, and we are looking for a student to be in the 5th grade. I don't want to put parentheses around that. This is our notation for part A. Just simply capital Y equals 5. Part B says to determine the probability that a student is in the 5th grade. That's probability of capital Y equals 5, and express the result in terms of percentages. So in this table, I already have the sum of all the students. And I've got to get to my sheet where I've already calculated this to save us some time. And we're looking at 5th graders. So again, just like we did in the previous example, for part B on this one, the probability that y is equal to 5. Again, it's the frequency over the population. The frequency in this case is 3,629 fifth grade students over 34,169 total students in the population. Well, I say that these numbers ignoring the fact right now that these are in thousands. So when we simplify this, we get 0.106. Part B does say to express the result in terms of percentages, so that is 10.6%. So what that tells us is that 10.6% of all elementary school students are in the fifth grade. And then finally, part C, it says determine the probability distribution of y. I'm going to go back to Google Sheets. Example 3. So here I've typed in all the values from the table. I have the grade levels and I have the frequencies. And I want to do the probability of x, big X equals little x. So first I want to calculate the sum of my frequency distribution. I know we already know the value, but just to refresh everybody's memory on how to calculate sums of columns, it's equals sum and then highlight the column. And there's our total. Then for the probability of big X equals little x, it's going to be equal to the frequency divided by 34,169. Hit enter, and then we can drag that down to the end of our table. And just to check our distribution, let's do a sum again. And that does equal 1. So there's our probability distribution. We can round these to 3 decimal places. We don't want to include that many decimal values on any probability distribution. So just for example, we have 0.141, 0.109, 0.108, 0.109 again, 0.107, 0.106, and I'm just going to check to see if that sum is still 1. I don't think it will be. It should be pretty close though. Yeah, see, so here's an example where because I rounded these values, it's not exactly 1. In a previous column, it is 1 because there is no rounding errors. The computer is using every possible digit that it can get. In our 4th column there, where we rounded to 3 decimal places, we do have the rounding errors, and so that's why our probability is greater than 1. But the principle is still the same, and it's going to work for the context of everything that we're going to do in this class. So part C, we answered that on the Google Sheets. We listed all the probabilities, and then we can go on and we can use addition to come up with probabilities. You can see right here already on part E, for example 4, it says the probability that x is less than or equal to 2. So there's going to be addition and subtraction that we can use when we're calculating some of these probabilities, and we're going to go ahead and see that here with example 4. So in example 4, it says use random variable notation to represent the event that exactly, that's a terrible typo, exactly 2 heads are tossed. So I've already listed all the possible outcomes. If you flip a coin 3 times, you can get 3 heads, you can get heads, tails, heads, and so on down the list. Use random variable notation to represent the event that exactly 2 heads are tossed. So for part A, big X is our discrete random variable. And we're just looking at the event where X equals 2. Part B, determine the probability of X equals 2. So how many times do we get 2 heads? We get it here, this 3rd option, the 5th one, and that's it. So we have 3 out of 8 possibilities where we get 3 heads, or 2 heads rather. So we can calculate that as probability of big X equals 2, our discrete random variable. We have a frequency of 3, and our population in this case is 8, but there's only 8 total outcomes. and that's going to be equal to 0.375. Find the probability distribution of X. Again, that's easiest to do with Google Sheets. So we go to Google Sheets, example 4. Here are the number of heads listed in column 1 is 0, 1, 2, and 3. The outcomes possible are 1, 3, 3, and 1. And then the probabilities, we need to do a sum. Should be 8. And so then the probabilities become the outcome divided by 8. And I typed that in incorrectly. It should be equals this cell divided by 8. And then I can drag that down. It takes each one of those cells underneath outcomes, divides it by 8, and we get our probability distribution for the discrete random variable X. Then let's see, what do we have next? I'm looking at the wrong question. Part D. So determine the probability, or write down the probability notation. Put on here, C was on Google Sheets. Now we're going to look at part D. Again, it's just notation. That's all it's asking for. Use random variable notation to represent the event that at most 2 heads are tossed. So at most means we could have 0 heads, we could have 1, we could have 2, but no more than 2. So in this case, we're looking at the probability that our discrete random variable is less than or equal to 2. And from there, we can actually do the calculation for that actual probability by referring back to our random variable table that we computed just a second ago on Google Sheets. And if I were to list this out, it's the probability that X is less than or equal to 2 is going to be equal to the probability that our random variable is equal to 0 plus the probability that our random variable is equal to 1 plus the probability that our random variable is equal to 2. So I take all 3 of those probabilities and I add them together, and I will get the probability that our discrete random variable is less than or equal to 2. So I have 0.125 plus 0.375 plus 0.375, and then that's going to be equal to 0.875. So there's an 87.5% chance that at most 2 heads will be tossed. So that would include, again, like I said, the values for 0, 1, and 2. And then that makes sense too, because if 3 heads are tossed, the probability of that is 0.125. If you add 0.125 to the 0.875 we just calculated, we do get in fact 1 as our probability total, which is correct. But we're only interested in this case the probability that the discrete random variable is less than or equal to 2. So it's just going to be a sum. And then we're going to go into our final example, where this actually wants us to take a simulation and basically simulate what happened in example 4. In example 4, we're using frequencies based off known probabilities. A coin only has 2 sides, heads and tails. If we simulated this, say, 10 times, if I flip a coin, I can get heads 1 time. I may get heads the 2nd time. But a frequency table would tell us that I should have expected to get heads the 1st time. Then that means I should get tails the 2nd time, because it's a 50-50 chance. But that's not real world. That's not a practical application. That's going to be a frequency interpretation of the known values of a fair coin. So what we want to do here for example 5 is suppose that we repeat the experiment of observing the number of heads, capital X, obtained in 3 tosses of a dime a large number of times. So large is a relative term. Traditionally that might mean 1,000 or more. Then the proportion of those times with which to say no heads are obtained, X equals 0, should approximately be equal to the probability that we computed using a frequency table. And what I've done, it says use simulation to verify these facts. What I've done is I've gone ahead and created random number table. We've done this before in class. We in this first cell, I defined it to be rand between. Remember, we've used that before. 1 through 8. I numbered each one of the possible outcomes that were listed in example 4, starting with the first one. I think it was 3 heads, or no, it was 3 heads. I numbered that one 1. I went down that list all the way down to 3 tails, which was numbered 8. So here in the first cell, I did a random integer between 1 and 8, and then I extended this out. I'm just going to do it again. Extended it down to 100, and then over 10 columns. So that gives me 10 by 100, which is 1,000 simulations of flipping these coins. And I've listed right here heads, 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 tails, heads, tails, heads, heads. And I've set up a count function under each one of these. You can see the equation up here in the formula bar. We'll talk about that more in class together as well, because this is one of those things where I'd much rather do this in person with you to help you understand how to set these up. But I set up these count functions under each one of the outcomes. And then down here in the next row, I have the probability that x is 0, which means no heads. Probability that x is 1, which is 1 head, and then 2, and then 3. And I've let the computer calculate those probabilities based off my simulation. We can see that the probabilities are actually fairly close to the frequency distribution table. They're not exactly the same, because this is a true simulation using just random numbers to indicate all of our possible outcomes. So I'm going to end it right here, because again, this example 5, I do want us to do this together in class to get some practice with creating simulations using Google Sheets, because it's going to become a lot more useful throughout the course of this unit. But I think that's probably the end of this set of notes. Yeah, we get into the homework problems. We'll talk about all the homework problems, or as many as we can during class. Answer any questions you guys have about these notes. And we'll just keep moving forward. So I hope everybody's having a great night, and I will see you in the morning.